In our previous three videos, we looked at the assumptions that are implicit in the ideal Atwood machine. Because these hidden assumptions require an understanding of dynamics that is typically unavailable to students seeing this problem in a high school or college sophomore physics class for the first time, they are often presented with a hand wave that can confuse students who are looking at the problem closely. We use these hidden assumptions to derive relationships between accelerations and tensions that allowed us to reduce a system of two equations with four unknowns to a system with two unknowns. We solved this system and then checked our answers to see that they made sense. In this video, we're going to look at other ways I've seen the problem solved in online videos and bring out a few details that often confuse learners seeing these techniques for the first time. In looking at various techniques to finding a solution for the acceleration of the masses, we'll pay particular attention to what sign convention is being used and how to interpret our answers relative to this sign convention and the assumed direction of our force and acceleration vectors. Now, in video 1, we introduced the Atwood's machine problem that was taken from the third edition of Surway's college text, Physics for Scientists and Engineers. We changed the problem slightly, however, and solved the problem where M1 was assumed to be greater than M2. Now, let's take a look at Surway's original problem where M2 is assumed to be greater than M1. First, let's look at the free body diagrams on the left. The forces are clearly marked and directions are indicated with arrows. Although we don't see the sign convention explicitly in the diagram, we can infer the choice of sign convention by looking at the equations provided in the solution on the right. Looking at the first equation, we see Newton's second law for mass 1. The fact that t is positive in this equation and is pointing up suggests that up is positive. This is reinforced by looking at the sign chosen for the net acceleration term on the right side of the equation. This is also positive, and the acceleration of m1 is shown as up, and agrees with our intuition that m1 would move up under the conditions that m2 is greater than m1. The same logic applies for the equation for m2. The tension is up and positive, the weight is down and negative, and the net acceleration is also negative and is assumed to be in a downward direction. So we can safely say that Surway has chosen a sign convention where up is positive and down is negative. This is exactly the same sign convention we chose in our solution for the case m1 is greater than m2. Now, I'll just make the parenthetical remark that Surway provides no indication of why the tensions or the accelerations should be the same. Further, we see that Surway solves the system of equations in a manner similar to the approach we took in video 1. Or rather, in video 3. However, instead of distributing the minus sign and adding equations as we did, Surway simply subtracts one equation from the other to eliminate the common tension term. He is then left with a single equation and he solves for the unknown variable a. Now notice in Surway's formula, the acceleration is slightly different than the one we derived in video 3. Our solution differs from Surway's solution by a negative sign. That is, his solution has m2 minus m1 in the numerator, where our solution has m1 minus m2 in the numerator. And we use the same sign convention where up is positive and down is negative. So who's wrong? Well, the answer is that both solutions are correct. First, the problems are slightly different because we made different assumptions about the relationship between the masses. Surway solved the problem where m2 is greater than m1. We solve the problem where m1 is greater than m2. But the difference in our solutions goes a little deeper than simply the relationship of the masses. It has to do with the choice of the vector directions in our diagrams as well. Now, this choice of directions was influenced by our assumptions about the masses. In both solutions, we assumed the heavier mass would fall downwards and the lighter mass would move up. These assumptions are embedded in our choice of directions in the free body diagram and in our system of equations. The point I'm hoping to make is this. The answer we get is always relative to the choice of directions we've assumed for our vectors. It is also relative to our chosen sign convention. If the solution is positive, our choice of assumed directions is correct. If our answer comes out negative, then our choice of assumed directions is backwards. That is, the object moves in the direction opposite to the one we assumed. I'm going to further explain this on the next slide, but before we leave Surway's solution, I want to point out that Surway's solution for T, the tension, is identical to the one we derived in video 3. So here we've reproduced Surway's solution for the acceleration from the previous slide. And it is true the answer is positive when m2 is greater than m1. And this means that our assumed directions for acceleration are correct. That is, in this instance, m2 would move down and m1 would move up. But what happens if someone came along, saw Surway's solution, and put in random numbers for the masses? For example, what would happen if someone plugged in m1 equals 5 kilograms and m2 equals 3 kilograms into Surway's formula? The numerator would then be 3 kilograms minus 5 kilograms, which equals negative 2 kilograms, and the answer comes out negative. The implication is this: since the answer is negative, it means that Surway's assumed directions need to be flipped. That is, m2 moves in the up direction and not in the down as assumed by Surway. Further, m1 would move down and not up as previously assumed by Surway as well. This result is also consistent with our solution derived in video 3. The numerator of our solution, found in video 3, was m1 minus m2. Using the same data points, the numerator would now be 5 kilograms minus 3 kilograms equals 2 kilograms, which is positive. This means that our assumed directions are correct. Mass 1 moves down, and m2 moves up, as we initially assumed. This point is subtle and tends to confuse first-time learners, so it bears repeating. Our sign convention always tells us how to initially interpret the meaning of signs when setting up our equations. The sign of our specific solution, however, depends on the chosen direction of the vectors in our free body diagram. If our particular solution comes out positive, then our initially assumed directions were correct. If our answer comes out negative, our initially assumed directions are backwards, and we need to flip or reverse them in order to understand how the objects are actually moving. Now, here's another method that I've noticed in several online solutions. In this approach, we are told that we can choose a sign convention where the direction of acceleration is always positive. Typically, there is no explanation as to why this is used. Many first-time learners are confused by this. At first blush, it appears to be rather arbitrary, because each mass has been given a different sign convention. This type of hand wave can be particularly stressful because it appears that the problem solver is using some advanced or a priori knowledge about the system, and rarely are we let in on the secret. In a moment, we'll take a look at the logic behind this approach and attempt to identify the origin of this approach. But before we explore the origins of this sign convention, let's first see whether we get a solution that makes sense. Again, let's assume m1 is greater than m2 as we did in videos 1 through 3. And we'll use the convention that the direction of acceleration is always positive. So we need to make some assumption about the direction of the net acceleration before we write down the sign convention. Based on our intuition of the system and our assumption that m1 is greater than m2, we show the acceleration for m1 to point down and the acceleration for m2 to point up. This means that for m1, down is positive and up is negative. And for m2, up is positive and down is negative. Again, this comes from the sign convention that the direction of acceleration is always positive, and our guess as to the direction of the motion of the masses. In this case, our guess is based on the given that m1 is greater than m2. Using our sign convention and Newton's second law, we can write our equations. For m1, the tension T is negative. The weight m2 times g points down, but is now positive. And m1 times a, the net acceleration, is also a positive quantity. For m2, the tension T is positive. The weight term m2 times g is negative. And the net acceleration m2 times a is also positive. Because the t terms have opposite signs, they will disappear when we add them. When we solve for the acceleration, we get the same equation we found in video 3. Since we are given that m1 is larger than m2, the acceleration is a positive quantity. As a result, the assumed direction of the acceleration for each mass remains correct. No change is necessary. So the technique seems to be valid. Now, let's see why. In another online video of the Atwood's machine, I saw a presentation where the problem solver drew a pulley, assumed a direction of rotation, presumably on some assumption about which mass was heavier, and drew arrows to indicate the direction of the masses. The problem solver then drew plus signs up along one side and down along the other. This sign convention is reproduced in the figure on the right. When I saw this for the first time, I was so confused I stopped watching the video. However, when I saw this same technique being used in another online video, I decided to pay a little more attention and figure out what was being done. So now on the left side of the slide, I've redrawn the free body diagram from the previous slide where we assume that the direction of acceleration is always positive. Now, the logic for both approaches comes from a third sign convention. And it is a sign convention we used in video 2 when discussing torques. That is, there's another sign convention based on the direction of rotation that says rotations in the counterclockwise direction are positive and clockwise rotations are negative. This notion comes from trigonometry where angles are positive when they are rotated in a counterclockwise direction. So torques would be written as positive quantities when they result in a counterclockwise rotation. And by extension, we would write that forces that drive a counterclockwise rotation of the pulley to also be positive. The point here is that the three approaches are all the same sign convention. That is, counterclockwise rotations are positive. If one were solving the problem where m2 is greater than m1, one could use the sign convention that all elements that drive clockwise rotations are positive.